We're given this equation. We want to find dy dx. So let's begin here. The derivative of cosine is going to be negative sine. And we know that we keep the stuff the same. But then we multiply by the derivative of the inside stuff. The derivative of x is just 1, and the derivative of y is dy dx. All of this mess equals the derivative of x, which we'll call just 1. Now from here, there are different paths you can take. I would do something different than what your teacher did, but just for the sake of understanding what they did, I'll follow the pattern that your teacher took. They distributed that, so that it gives us So here's what I have. I distributed this term to both of these, and I got two separate terms. The one is there. I added this term across to the other side. That became here. This stayed there. Then I divided both sides by negative sine of that. I dumped that down below in the denominator, and I kicked the negative out to the front. So what you can now do, recall that generally speaking, a plus b over c can be expressed as a over c plus b over c. Let's apply this idea to this here fraction. 1 over that is here. And I kept addition, and then I said this over that addition. And the reason I put parentheses is because before it was one fraction, now it's 2. But the negative applies to both fractions because initially the negative applied to this one fraction, but this broke up into 2. And if you want, you can distribute that. But of course, know that this is just 1. Yes, that's just 1. So I have this here. That's just 1 times the negative is negative 1. And then remember that sine of theta is the same as 1 over cosecant theta, or similarly, cosecant theta is the same as 1 over sine theta. So this here, which looks like that, can just be rewritten as cosecant of theta, where theta is that there. And this is the final result. And yes, please forgive me if my hands are a bit dirty. I'm doing some more of those crazy customs. Find dy dx given this equation. But before we dive deep into that, a quick FYI. So recall from pre-calc that tangent squared theta plus 1 equals secant squared theta. I'll leave that there. We'll probably need it. So let's try this now. Let's find dy dx. So the derivative of tangent is secant squared. You keep the theta the same, but then you multiply by the derivative of that, which we saw is 1 plus dy dx equals 1, because that's the derivative of x. And then if you want from here, we can do what we did before, where we distribute that to that. Personally, I would have done something a little different, but the path that I took is not necessarily faster or simpler than what your teacher did. It's just a matter of different people do different things. Let's see, so I distribute that and I get this. Let me subtract this and then let me divide by that to get dy dx alone. Now check this out. Why don't we consider a manipulation of this here? What if I move this here to this side, and what if I move that there to the other side? What would that identity say if I made those modifications? Wouldn't it say something like 1 minus secant squared theta equals negative tangent squared theta if I made those movements? It seems kind of weird, and it is, but it's useful in this problem because now you can see that this numerator looks just like that. So by substitution, this gets replaced by that. So let's see. The numerator, which was this manipulation, turned into that there. Instead of theta, we wrote down what theta is, x plus y. And then the denominator used to say secant squared. But recall the original identity, secant squared can get replaced by this, which is why that appeared here. Now, what if I keep the negative in the front? And what if I write this as tangent of x plus y bracketed squared over tangent of x plus y bracketed squared plus 1. So if you're wondering what all this was me just playing around. I was just doing some math thinking that this would be necessary, but it's actually not. So ignore all of this in black. And then I just rewrote this as tangent of that there, but the square I put it on the outside because it makes it easier for my eyes to see that tangent x plus y, it actually equals x based on the original problem. And we can make those substitutions here and there. So watch what happens. We have dy dx equals negative, and then that's just going to be x squared. And that's going to be x squared plus 1. And I believe that this is what the teacher said was the result, and it is. So the goal here is to find dy dx of this expression. I would immediately rewrite this in a slightly different way. I'll keep tangent, but instead of writing arc sine, I would write sine inverse of x because they are one and the same thing. And I also prefer this style because it reminds me of something. And this is what it reminds me of. Remember that anytime you have like sine, cosine, or tangent, or any trig inverse of some object, the result is an angle. Sine inverse of whatever is an angle. And so let's just keep that in mind. And now what I'll do here is what I can do is I can take now the sine of the left and I can take the sine of the right. And I do this because sine and sine inverse knock out. So it's just x equals sine of theta. And I can reverse the order and I can drop a 1 below the x because I can remind you about so, ka, toa, where for sine, you have opposite over hypotenuse. So the numerator is my opposite, and the denominator is my hypotenuse. Now, opposite hypotenuse of what, Mr. Lee? Of a diagram where you, in first quadrant, where you have your theta here, and so theta is there, and sine of theta is opposite over hypotenuse. So from here, my opposite is this, which is x, because that's the numerator, and the hypotenuse is 1. The missing leg is called question mark, but we can go back to middle school and go Pythagorean Theorem because this is a right triangle. So we have question mark squared plus x squared equals 1 squared. Remember that? A squared plus b squared equals c squared. So question mark squared equals 1 minus x squared. So question mark equals the square root of 1 minus x squared. So that completes the diagram. I wipe out the question mark and I replace it by 1 minus x squared. This information is highly necessary. And that's actually what I was doing in the other problem. Where is it? I have so many papers here. It's what I was doing in the other problem there, but I didn't show you because we didn't need this idea for the previous problem, but we do here now. So watch what I do. Let's go back to the main problem. dy dx tangent. So what am I supposed to write in there? Sine inverse of x. So you know what I'm going to write instead? What it happens to equal, which is theta. Now this is good and bad. It's good because it's less writing, but it's bad because I want to find dy dx and there's no longer any x's or y's, it's just thetas. But it's all good because now we can take the tangent of theta, where theta is this angle here. And so I'll try it in green here. What exactly is tangent of theta equal to? Well, theta is there. I just have to hit it with the tangent function. Tangent is opposite over adjacent. So from here, my opposite is x. And my adjacent is this part down there. And so now we know what tangent of theta equals. Tangent of theta equals that. So this green can replace this by substitution. So we have dy dx of x over, I'm going to write this 1 minus x squared to the power of 1/2. Square root 1/2, same thing, power. Same thing. So now let's hit this with a quotient rule, as you were saying in your remarks. So dy dx, or actually, since we're actually going to take the derivative now, I'm just going to scratch that off. You see, I kept dy dx because I never did any calculus. I just did algebra and I made substitutions. Now is the time to find the derivative, which is why the dy dx vanished. So, quotient rule. the bottom times the derivative of the top. Well, the top has a derivative of 1. So it's just 1 minus x squared to the 1/2 power. Bottom derivative top minus the top times the derivative of the bottom. So what's the derivative of this? Well, hit it with the power rule. So the derivative of that is going to be 1/2. 1 minus x squared to the negative 1/2 times negative 2x, which is the part that many students accidentally forget to write down. Remember that? Because the derivative of that is, okay, you do the power rule, you keep that, you subtract 1, but then you immediately multiply by the derivative of the stuff inside of the parentheses, which is negative 2x. So all of this over the bottom squared by the quotient rule. So if you square the bottom, it's just this. Let's see. So this is one giant term. Negative times negative is positive. 1/2 times the 2, they knock out. X times the x is x squared. So here I have equals the square root of 1 minus x squared, addition, and it looks like this is going to be x squared over square root 1 minus x squared over this. Now let me explain myself, yes? So that piece is that. X times x was x squared. This bit had a negative power, which is why I dropped it to the bottom and the power became positive. And of course, I just used a radical instead of a fractional exponent, and that's here. Now what I can do, there's a 1 there, and now I can get common denominators. I can multiply top and bottom by 1 minus x squared, square rooted like that. And let's see what this gives us. So this is 1 minus x squared plus x squared over the square root of 1 minus x squared all over 1 minus x squared. Let's see if you agree. So that times that is just the stuff inside because the square roots knock out, which is why it's here. Plus x squared is that. And I turned 2 fractions into 1 because I had a common denominator, which is that. And now let me write this here. So these terms actually knock out, convenient. The 1 is all that's left above that, all over 1 minus x squared. If it's okay with you, I'll put a 1 here, and then I'll rewrite this in a different way. So I put a 1 underneath, and then I did that thing where instead of dividing, you multiply, but you take the bottom fraction and you reciprocate it, which is how I got this. The 1 is just 1. And I rewrote it like that into that. And then recall properties of exponents. These are the same thing and they're being multiplied. So you add the powers. 1/2 plus 1 is 3/2. So that's the answer. But then they're being kind of picky and they want this to be in the numerator. So this term comes up to the top, but you switch the sign of the exponent, which is how they got this here as their final answer.